Hey everyone, welcome back. So today we're going to be solving Leetcode 2593. This is actually problem of the day for today, and this is a medium level problem. I'll be ideally solving it in Java, but the concept would remain the same across all the languages. So I'm going to solve this a bit differently. There are a lot of ways to solve this. You can use maps, heaps, or anything else that you feel is capable. But I'm going to solve it a bit differently. So I hope you like the approach, and so let's begin. Okay. So the problem here states that you're given a certain set of algorithms, and you'll have to process all these algorithms and then return an answer. So the algorithm mentioned is that so you have an array called as nums, okay, and then you have values in that, okay. Now you are uh, you are supposed to find the smallest element in this particular array, okay, and once you find the smallest element, you're supposed to mark that element. Okay, let's say that the smallest element in this array is 1. Okay, I'm supposed to mark 1. Okay, and also you're supposed to mark the adjacent elements, right? So while I'm marking 1, I'm supposed to mark 2 and 3 as well. Okay, and after marking these, let's say that these are marked. Now in the unmarked section, in the unmarked region of the array, I need to find the smallest element again. Okay, what is the smallest element over here? It's 2, right? So what I'm going to do, I'm going to do the same thing again. I'm going to mark it, but there is no element towards the right, right? So I cannot mark any element towards the right. I'm supposed to mark the adjacent element, but there's no element towards the right. So what will I do? I'll just mark the element towards the left. Okay, now we have 1 2 3 marked and 5 and 2 marked. Okay, now again we have to find the smallest element in the unmarked region. Okay, again we find 4. So now what would be the final answer? The final answer would be that whenever you find the smallest element in the unmarked region, you add that particular value to the final answer. So first we have added 1, then we have added 2, then we have added 4, which gives the result 7. Okay, so this is a question, and these are the rules that you can apply, and we need to figure out a way to give the final answer. Okay, now let me write it down, and then let's look into the examples. Okay, let me take the first example itself. 2 1 3 4 5 2 2 1 3 4 5 and 2. Okay, this is the array, right? I'm going to mark it, I'm going to index it. Okay, now tell me something. So obviously when this question came up and you read the question, the first thought that would have come to your mind is that, hey, why can't I sort it? Right, I mean, even I had that thought. Why can't I sort it? Let's see why we can't sort it. Okay, now let me find the answer visually, then I'll sort it, then let me find the answer for that. Okay, now for this particular array, the answer would be 1, score would be 1, and then this entire thing will get marked. Okay, now the score will be plus 2, this entire thing will get marked. Now the score will be 4 plus 4, now this will get marked. What is the output that I got? Is 7. Perfect. Now let me sort it. This is the sorted array. Okay, you get 1 2 3 4 1 2 2 3 4 5. There are n number of reasons why you're not supposed to sort it, because it says that you have to make the adjacent element marked, meaning whenever you're given in a problem, you're given that you have to do something with the relative order of the elements. Here you're dealing with the order, right? You're marking the adjacent element of the smallest element, right? So you're considering the relative order of the element, right? Whenever you're considering relative order of the element, you can never sort it, because if you sort it, the index itself of that element will be changed, right? Then there's no point of us solving the problem, because the whole problem changes, right? That is one of the main reasons. But let's look at it in the example why we can't sort it. Another reason why we can't sort it. Okay, come 2 3 4 and 5. Okay, now let me find the smallest number 1. Okay, mark 2. Okay, what about the next one? Score is 1. What is the next one? 2. Right. So I mark it 2. What about the next one? 4. I mark 4 plus 1. 7. Okay. Now I'm like, hey, you said that you can't do it, but we can do it. Right. Let's take another example. 2, 3, 5, 1, 3, and 2. Let me index it 0, 1, 2, 3, 4, and 5. Okay. Now, what is the smallest element? 1. Let me mark it. 1. This will get marked. What is the next smallest element? Okay. And another point that I forgot to mention is that whenever you have two same elements, for example, we have one 2 over here, another 2 over here. So now we need to know which element to choose. Okay. Here it's mentioned that choose the smallest integer of the array that is not marked. If there is a tie, meaning if there are similar elements, choose the one with the smallest index. Okay. So in this example, what is the smallest index? 2. So what we're going to do is we're going to mark 2. So we're going to mark 2 and then we're going to mark the adjacent elements. Now what is pending? 2 is pending over here. Be plus 2. So we're going to mark this as well. So my answer would be 5. Right? Now let me sort it. Okay. This would be my sorted array. So it'll be 1, 2, 2, 3, and 5. Okay. If I index it 0, 1, 2, 3, 4. I'm missing something. Alright, I missed a 3. So 3, 3, and 5. This would be index 4 and be 5. Perfect. Now, let me find the smallest element. 1 is the smallest element, so I'm going to mark 1. Okay. So I'm going to take 1 over here. Next smallest element which is not marked is 2. I'll mark 2 and 3. So I'm going to take 2 over here. Plus, what is the next smallest element which is not marked? 3. So I'm going to take 3 over here, whereas it's supposed to be 2. I'm taking 3. So my answer changes, right? So this becomes 6. So I'm going to mark this. I'm going to return 6. Right. So now we got to know that we can't sort it. We can't sort the original array. Right? We can't sort the original array. But can we say that it has to do something with sorting only? Because you're finding the smallest element, right? Always. Right. So we know that it has to do something with sorting. Okay. So now we need to figure out a way where we can leverage sorting and then find the answer. We can leverage sorting in a way that the relative order of the elements is not changed. That is the main goal. Okay. So that's exactly what we're going to do. Again, my solution is a bit different from others, I believe. So you can use a lot of data structures. You can use heaps, or you can use maps, or you can use whatever that you feel is comfortable. But this approach is also pretty optimal, and it will give you another idea on how this can be done. Okay, and that's exactly what I'm going to do. Okay, now what would be the time? Let's go through the brute force first before we get into the optimize. What would be the brute force solution? Okay, can I say if I have the array that is 2, 3, 2, 3, 5, 1, 3, and 2, can I say that I can find an element 3? Okay. Now for that element, okay. No. First, what do I need to do? I need to find the smallest element in this particular array. Right. Now I found 2. Okay. After finding 2, I will mark the adjacent elements. Now the adjacent elements is marked. Maybe we can remove it. Maybe we can create an array list, copy all the elements. Okay. And then copy all the elements. Not this 2 actually. This 2. Because the smallest index is this 2. Okay. Maybe what we can do is, since array list is also contiguous, we can create an array list, store all the elements, and then maybe find the smallest element. Okay, remove the adjacent elements from that, and then in this part of the arrays, find the smallest element again, iterate through the entire again, find the smallest element in the array, and then remove these 2 in that, and then iterate through the array again, find the smallest element again, and then my bad, this would be the smallest element, right? Yeah, so find the smallest element, remove the adjacent elements from that. Okay, you will get an array which will look something like this. Then what you do is remove this particular element. So you'll remove 5 and 3, right? Move 3, yeah. If I remove 2, my 3 also will get removed. Then I have 2 left. Then I will add that. Then I'll remove 2 as well. Okay. Now, what would be my time complexity? If you have an entire array of size n, okay, first you're going through n, okay, then ideally you're doing either n minus 2 or n minus 3, because you can remove 3 elements as well if it's in between. Okay, then from n you're going to n minus 2 or n minus 3. Then ideally it's the same thing, n minus 2 or n minus 3. Then you keep on going until you get 0, right? The array length will become 0. Now that is one. And also you will be copying the array, right? I mean, every time you're removing, since array is stored in a contiguous part of a memory, you can't just remove the elements. So ideally what array list would do is it will copy the elements into the new array without the elements that you try to remove. So copying, I mean, array list has a time complexity of amortized O of 1 for adding the elements. For adding new elements, on average it's O of 1. But if you're removing elements, then in that case it'll be O of n, because you'll have to copy the elements. Right? So for removing you'll get n, and then you'll be iterating through the array again and again and again. So that will be n. You'll get a solution for n square. Okay. This is my idea. Ideally I would do it this way if this was brute force. So this would give n square. And n square is not ideal because you have a constraint that is given to you as 10 power 5, right? So if it's n square, the worst case, if it's worst case n square, after removing all those small order terms, it will become 10 power 5 into 10 power 5. You'll get it as 10 power 10, which will throw you a TLE. This will give you a TLE. Okay, so we can't use that. Now we have to think of a solution which is lesser than that, right? Now let's come back to the thought process that we were in. We said that, hey, this cannot be sorted. Of course this cannot be sorted, but it has to do something with sorting, right? It has to do something with sorting. So can I say that, let me write it down. Can I say that I have to maintain the relative order of the elements, but still I can sort? How is that possible? Right. So what are we doing visually first? Okay, first we're looking at 1. Okay, we are removing it, marking it. Now we're not even looking at the marked elements. Let the smallest be in the marked elements only. We're not even looking at it, right? We're looking at the unmarked space, and then we're looking at the smallest element again, right? So we're looking at 2, right? Now we mark it. Now we're not even looking at the marked region, we're looking at the unmarked region, and the smallest element is 4. Right. So again and again you're finding the smallest element only. Okay. Maybe the next smallest element, but you're finding it in a unmarked space, not in a marked space. Okay. So can I say that if I sort this particular array, okay, I mean, can I say that if I sort this particular array with respect to the index of each element, in that case I will know which element is the smallest element. At a given point I'll know which element is the smallest element. Okay, I mean I'll go through it, but just think about it for a second. We have to think about sorting it in terms of the index. We are sorting the value itself, but we'll be sorting the index of the array, not the value directly. So by that what I mean is, if I have an array with the index of all the elements, the index would range from 0 to n, right? So we would have index of all the elements 0, 1, 2, 3, 4, 5. Okay, this is a new array. This is an index array. So we have index of all the elements. Now I'm saying that I will be sorting this index array based on the value provided in the nums array. Okay, by that what I mean is, we will see how to sort it. We have to use comparator. It is not normal sorting. We have to use comparator. We'll see how it is. It's very interesting. But for now, just understand that we'll be sorting it. Okay. If we sort this array based on the index, what will we get? What is the smallest element? Smallest element is 1. So index of that is 1. Okay, I'm sorting this array. Right. Next, what is the smallest element? 2. We have two 2's over here. We have to pick the smallest index one. So I'll mark 0. It is at 0. Then it is at 5. Then it is the next smallest element is at 2. Next smallest element is at 3. Next smallest element is at 4. Okay. This is the sorted index. 1 0 5 2 3 4. Perfect. Okay. Now that I have the sorted index, okay, I will, for each value of this, so this is basically a sorted array itself, but the sorted array contains an index, not the value. So at, now I know that at index 1, okay, there is the smallest element. At index 0 is the next smallest element. Index 5 is the next smallest element in the non-decreasing, in the ascending order. Okay. So now how can we leverage the sorted array? Let's take a look. Let me delete this particular array. Let's see. Now what I'll do is now what I'll do is we don't need to index this. Okay. What will I do is I will find the element at index 1, which is 1. Now I know that, hey, this is the smallest element in the array. Okay, find the index 1. Now what will I do? I'll mark it. I'll mark all 3 and I'll increase my count. Score. Score will be 1. Okay, now I'll come to 0. 0. When I check 0, I have marked it. Right. So there's no point considering it. So what can I do? I can ignore it. So this won't add to my score value. This will just get ignored. Okay. Next I'll go to 5. What is that? Index 5. 2 is at index 5. Okay. So here what I'm going to do is I'm going to check if it's marked or not. It's not marked, which means that I can mark it. So what I'm going to do is I'm going to mark 5 and 2. Okay. Now my score is increased by 2. Okay. Next I'm going to go to 2. What's at index 2? 3. Is it marked? It's marked. So it's of no use to us. So I'm going to scratch it off. Next I'm coming to 3. What is it? Index 3? 4. Is it marked? It's not marked. So I'm going to add it. Okay. And then I'm going to mark it. What's at index 3? 3. It's marked. So it's no use of me. No use for me. I'm going to go to this one. Okay. Next is what? 4. Index 4 is at 5 is at index 4. It's of no use to me because it's marked. Now I'm going to return my final score as 7. Is this the expected answer? Yes, it is. The final answer is 7. This is the approach that we're going to follow. Okay. Now, what is the time complexity for this approach? What is the time? We are going to be sorting it. We're going to be using arrays.sort, but we're going to be writing a customized function which we want, which would satisfy our requirement of sorting. So again, sorting will be NlogN. Plus you'll be iterating through the index array once, so it'll be n. So this will approximately give you NlogN time complexity. Okay, what about space complexity? I'm creating an array with all the indexes. So if the range is still n, that is whatever the value is, I'm going to create an index till n. So my space complexity will also be, not also, but space complexity will be O of n. This would be my approach. Right. So we've optimized the time complexity and also the space complexity, because either ways we'll be using space, but the time complexity is optimized. Right. Now, is that the best time complexity we could get? I believe so, because in the editorial also, if you've seen, the best time complexity that we could get is of NlogN and then of n. This is your, I believe this is our, optimized solution, because I don't see anything after that. Right. So we are not using heaps, or we're not using any of the other data structures like map and all that. We're just doing it with arrays, uh, and the answer, I mean, we would still be able to do it successfully. Okay. Now, the main part is coding. How do we write a comparator function according to our logic? Let me show you that. This is the important part. Okay. Now, the first task is for us to create a integer array which it stores only the index. So let me say, let me actually, okay, integer of, let me call it index yara equals to new integer of nums.length. Okay, perfect. Now what we're gonna do is we're gonna iterate through the this thing, I less than nums.length, and then I plus plus. What we're gonna do is index I mean, does not require index array of I equals to I. So this I means that we are holding only the index. Now we're going to sort it. How are we going to sort it? Let's take a look. We're going to write the same thing, arrays.sort, and then we're going to include our index array. Okay, now index array. Now we need to write a new comparator function. So I'm going to call the comparator class to comparator class. I'm going to call the comparator class, and then I'm going to give it as integer. Okay. If you've seen the comparator class, it contains the compare function, and that is the function that we're going to override. So it's going to be public int compare. Okay. And it's going to take integer two variables, integer a and integer b. I would suggest you to go through the comparator. How do you write a comparator? But I will give you a brief. I mean, I will tell you what it's doing. But I would suggest you to go through the comparator to get a better understanding. Okay, and try solving problems on that. So what I'm gonna do is okay. Now what I'm gonna do is see. It's let me take it as okay. Now it's simple. So what does sorting mean? Ideally, on a very high level, what does sorting mean? It's comparing two values, okay, and based on the type of sorting, it's gonna assign that value. Meaning, if you're sorting the array in an increasing order, and if you're comparing A and B, if B is greater than A, so it's gonna first put A, then it's gonna put B. Ideally, that is what sorting is doing, right? That's exactly what we're gonna do. So what we're gonna do is, if A is let me comment it out. Okay, if A is greater than B, okay, which means that B has to come first because we're sorting it in ascending order. So what will I return? I'll return -1. This is the return. This is the return. This is how you're supposed to return to a compare function. And every time when you're comparing two values, based on what you want, you return either -1 or 1. Okay. Else if B is greater than A, which means that I want A to come, so I'm going to return 1. Okay, so the compare function will understand, hey, if I'm getting -1, I have to put A first, sorry, B first. If I'm getting 1, I have to put A first. Okay, that's exactly what we're going to do. But how we're going to sort it? We're going to sort it with the value of that index in the nums array. So what we're going to do is, if nums of A is greater than nums of B, so I'm going to return -1. Else if nums of B is greater than nums of A, I'm going to return +1. Okay, meaning that A has to come first. Okay, now Now we have included the scenario for a greater than b and b greater than a. What about the scenario where a equals to b? For example, we saw here in the input array that there are two values which are equal. Now how do we write a comparator for this? In the question it's given to that we have given to us that you have to return the smallest value, either 0 or 5. Based on the not either 0 or 5, we have to return 0 because that is the smallest index compared to 5. Okay, and that's exactly what we're going to do. Okay, else if, so what is a and b? A and b are the index itself, right? So this I can easily compare. If a is greater than b, I'm going to return -1. Okay, else if b greater than a, I'm going to return 1. Right. Okay, simple. Now this is done. Let me remove this because we need to have a return outside the if and else condition. Okay, now done. Okay, now let's see, before we give the solution, let's return a dummy value. Let's return anything. 2, 1. Okay, 1 also 2. Let's return a dummy value where we'll say that return dummy value so that I can show you if this comparative function is doing what it's supposed to do. So what I'm going to do is I'm going to iterate through the so this is sorted now, so I'm going to iterate through the index array, and then I'm going to print the value just to show you how it's working. Let me run it. Okay. What is the sorted array that we got over here? 105, right? Okay. 2, 3. Nums of a greater than nums of b. Teacher A, teacher B. Or is this the other way? I'm not sure. One second. Right. My bad. Just a small correction. So if a is greater than b, in that case, b has to come first. So we're returning 1. So if a is greater than b, meaning that b has to come first. So we return 1. Okay. If b greater than a has to come first. We return -1. So just remember this, if a has to come first, we return -1, else we return 1. Okay, if b has to come first, we return 1. If a has to come first, we return -1. Okay, so now let's see the output that we got for this input. The output that we got over here for this one, we got 1 0 1 0 5 2 3 4. Let's compare it. 1 0 5 2 3 4. Perfect. So now we know that this is working as expected, and this is how you write a comparative function. Okay, now we're iterating through the value. Okay, now we're iterating through the value of the index array. So what is value? It's nothing but the index arranged in the ascending order. So what we're going to do, we're going to check. Okay, so first thing what we need to do is, we're not even going to process it if it's marked right. So we need to check if it's marked or not. And how do we mark something? You can mark it with anything. It's your choice. See, what I've done is, your nums of I is ranging from 1 to 10 past 6. So there won't be any negative value. So I marked it with -1. Okay. So what I'm going to do is, I'm going to check if nums of val equals to minus 1. If it's not equals to minus 1, only then I'm going to process it. So I'm going to have something called as int score equals to 0. Okay. Then what I'm going to do is I'm going to take score plus equals to nums of val. Okay, now I have to mark it. So I'm going to say nums of val equals to minus 1. Perfect. Okay, now what do we have to do? We have to mark the adjacent elements. Okay, but there is an edge case to that. Why? Because if you are at the, let me erase this, 2314 2 1 3 4 5 and 2. If you're at the end or if you're at the starting, you don't have an adjacent element to the left for this, you don't have the adjacent element to the right for this. So if you don't handle it carefully, you're going to get a index out of bounds exception, right? So we need to handle that. So what we're going to do is first we're going to look into the hyperpath. We're going to check if val not equal to nums dot length minus 1 and val not equal to 0. What we're going to do is we're going to mark the adjacent element as well. 1 equals to minus 1. Nums of val plus 1 equals to minus 1. Okay, else if val equals to 0, then we're going to mark only the right side element, that is nums of val plus 1 equals to minus 1. Okay. Else if val equals to nums dot length minus 1, then we're going to mark the left element, nums of, because there's not going to be a right element, minus 1 is minus 1. Perfect. Okay, now this, I think the return type is long, so this is supposed to be long and we're gonna return score over here. Okay, so this is done. So if my nums of value equals to minus 1, then it's gonna skip it, it's gonna go to the next value. Perfect. Now what if the length of the element is 1? You're gonna handle that as well, right? That's very simple. So what we're gonna do is we're gonna say that before all of this, let's make a check. If nums dot length equals to 1, what we're gonna do is return nums of 0, because that is itself is gonna be the minimum element. Okay. Now let me run this. Let's see how it works. Okay. Perfect. Let me submit it. Perfect. So okay, I need this thing, but if you do it mathematically, this would be your time complexity and this would be your space complexity. I hope you have understood the solution. I would suggest you to go through the solution again and try doing it on your own. And yeah, thank you.